Welcome to the final week. The plan is that we're going to meet in Vodi 114. Anybody had a class meet there before? Previously? I think it's 100 level, going to be first floor, and be cool if we had a couple volunteers to be there maybe like 10 minutes early to help me set some stuff up. So you don't have to raise your hand, but just cool. Great. Thank you. A few of you who are there are a few of you usually here a few minutes early. So that's going to be fun. I have a quick video to give you a sense for what that's going to be all about. So back when I first started doing this experiment in chaos, Darren Hitt in engineering had this cool new camera that takes pictures 20,000 times a second, and we thought, well, let's use it for something. We might as well point it at some oobleck in the speaker and see what happens. So this is a video that we made back then of what this cornstarch and water mixture that we're going to play with on Thursday, what it looks like in slow motion. So, and there was this thing, this cartoon audio called Extra Normal back then, which I don't know if it's still around, but I typed out a script for this robotic voice to read over the top of this slow motion video. Fun. Okay. Hold on, we got to start over here.
We begin with a mixture of cornstarch and water with food coloring added for contrast. The fluid is shaken at 60 Hz in a subwoofer. As the acceleration of the speaker cone increases, Faraday waves give way to the localized protrusions resembling a boiling biological liquid. The non-Newtonian black is a shear thickening fluid, acting like a solid when in contact with the speaker. For more installments of recreational truth, visit onehappyearth.com.
Okay, so that's going to be a fun experiment. We're going to do that on Thursday. It's we'll break into groups of 4 because that's how many speakers I have, and we'll try not to burn anything down over there. But we're in a contained area, so that's kind of the idea rather than doing it in here. They do experiments over there. So that's on Thursday, and on Thursday I will be giving you the final exam. So you're going to turn in homework 12, and you'll take this final, and then you'll have a week to work on this exam, and then hand it back in to me in my office by, say, 10 a.m. a week from Thursday. Josh. I think that's this exam. Another exam. You're double booked. Oh, well, it's up to you. You can come at 6 a.m. You can turn it in Wednesday, or you can march over after your double booked exam at 10:45. That's okay. That's not the end of the world. Yes. They shouldn't assign you 2 finals at the same time. Things that are obvious. Other questions? All right. So I'll have some office hours after class today to talk about the homework if you're working on it and wondering. So let's see. Other updates from Twitter. We have a cool new experiment over in Farrell. This is a inverted pendulum. So you remember that the pendulum that stands on its head, that's an unstable equilibrium. It's actually a saddle because if I can find initial velocities to throw the thing with, which will have it land pointing straight up. But that's a measure 0 set of conditions in the 2D state space of the pendulum. This has got a little actuator on it that so Hamid Osare, who's a faculty member in electrical engineering, is working on. I think he's teaching a class on control theory. So control theory was this this field was basically invented in the 60s to steer missiles. So you got these fins attached to the back of the missile, and you want it to go in a particular location, but it's going so fast that you can't send observations back to the computer that can crunch and decide, well, we should turn left or turn right. It has to kind of happen on board. So they needed a really fast method for taking observations about the state of the system and making adjustments. And so there's a whole set of linear algebra tools to do that under this heading of control theory. And it's used all over the place now in engineering. It's also used to predict the weather because just like with fins, you want to know kind of where the missile is going to go. You want to make adjustments to what our forecasts and our best guess of the atmosphere look like when you get new observations. And so the same ideas from control theory are used to try and synchronize forecasts of the atmosphere with the actual behavior of the atmosphere, just like they are for the same types of methods. They scale kind of horribly with dimension though, so people are still working on that. Anyway, so here's this system is attempting to keep this unstable equilibrium point vertically. They're attempting to keep it stable by wiggling this angle here. And so when I poke the bottom of the pendulum, it adjusts really quickly in the opposite direction to keep it standing up. And if you hit it too hard, it kind of freaks out and falls down, and it would hurt itself trying to get the thing to swing back up again. So I poked around and found some cool examples where people do this with double and triple pendulum. Some sweet background music, it sounds like. So the idea here is this is a saddle equilibrium, and you want to find the manifold that will make it stable and stay near there. And so this is a control theory algorithm. There's laser shining on probably 3 different parts of this pendulum, and then giving feedback to the motor so that the vertex can move in response to observations that the state is becoming unstable. So the motion of that, in the dark, you gotta kill the light. So this motion isn't prescribed beforehand. This is a chaotic system, and so you couldn't tell the motor what to do beforehand and just let it go. But because it's taking in observations of the state of the system and it's able to make adjustments to its behavior in response to those observations, the chaotic behavior can be controlled. So there's a whole field adjacent to what we've been learning about called controlling chaos. There's a book called Controlling Chaos written by colleagues of Jim York, who wrote this book. Ed Ott was another faculty member at Maryland who worked on that problem. Cool.
So is that is it machine learning essentially, where they have type of machine learning where they have a reward for success, and basically the computer's figuring out the algorithm, so it's kind of a black box? Or are people actually saying, when this happens, I mean, there's an infinite number of angles and such.
Yeah.
I assume it's an algorithm that's kind of black box.
Yeah. So Andy's asking about what's under the hood here. Is it some sort of fancy machine learning thing that figures out what types of motion to do in response to the perturbation it's receiving, and Or is it something simpler than that? And the answer is, so it is actually a lot simpler than what you are probably thinking of as machine learning, in that it's a white box. You could open it up and see, oh, well, in response to being pushed this way, the pendulum, in order to not fall over, the motor moves the base this way, and it's, so there are principles that it doesn't know, the algorithm that is being run, this control theory algorithm. One common one is the Kalman filter. It doesn't know about what you're going to do to it, and it's not learning that over time. It's just it's aware of the relationships between the variables, the thetas and the theta dots. There's a big matrix that represents their covariance. And then in response to observations, it knows which direction. It's kind of built into the linear algebra what it should do in response to observations that it sees. These control theory algorithms, some of them are integrating 100 potential futures of the pendulum and picking the best one. That's sort of a fancier thing to do. And that's more like what the weather prediction model is doing. But, in this case, the physical principles that underlie the behavior of the experiment are known really well. And still there's this great paper from about a decade ago now where Hod Lipson and some people, including Josh Bongard here at UVM, figured out how to evolve the differential equations from first principle, without any knowledge of gravity or physics or F equals ma. And so that process of that software is called Eureka. This company, Newtonian, started by Michael Schmidt to commercialize it. So that software is doing something more special than what I was describing with the Kalman filter, in that it can learn new systems that it doesn't know anything about pretty quickly, how to be predictive. And yeah. It's white box. That's right. Yeah. I mean, it's the equations. Yeah, the equations of motion for this Kalman filter, they're just a bunch of linear algebra, and the problem gets to be when the dimension is very large. So in the weather model, if you got 10 billion variables, computing a covariance matrix of a weather model, you got 10 billion by 10 billion. That's a lot. Let's do the math. That's 10 to the 20 entries in a matrix like that. 10 to the 10 rows, 10 to the 10 columns. And so doing any sort of linear algebra on that, God forbid, trying to find its inverse or using, doing a linear system solve would be impossible. So what you end up doing basically is assuming large blocks of that matrix are 0. So this variable, like the temperature outside the building here and the humidity in Japan, on average, they're not correlated. So that entry in the matrix would just make it a 0. And so that helps. That's called covariance localization. That helps make this more tractable. Now, other questions? There are whole packages, linear algebra packages, typically written in Fortran back in the 70s to do sparse matrix algebra, linear system solves and things like that. And there's some of the fastest things that we've created as, in applied math, because they need to be done so often. Something like 3/4 of all computing cycles done at, let's say, at the National Institute of Standards and Technology or some other government lab are linear system solves. So there's something that it's like the inner loop, and so people work really hard to get it to be really fast. Okay. Okay. So let's see, what else to say? We've been talking about the Lorenz equations. Oh, so Jim Bogro came and gave a nice lecture on Thursday about networks, an introduction to networks. I'll say that his class, data science, he has 2 classes, introduction to data science, and then that's sort of like a math, or it's a stat 287, and then a graduate version 387. I think that's fall, spring, typically. Great class. If you're looking to, get into that area, you like what you heard, and I mean, it's an incredibly interesting way of looking at how large-scale systems function. complex networks. Jim's class is on data science, and it sort of, these classes I'm talking about, they will teach you how to scrape data from the web and build visualizations of it. And then Peter Dodds teaches a class on complex networks, a spring class. It's a follow-on to the complex systems class in the fall. All great things if you have room in your schedule for this stuff. Any questions or comments on Jim's talk from last week? If you missed it, it's on the web. He's looking for students to do research on this sort of stuff. Lots of interesting projects he's involved in. So, okay, so we were talking about a week ago the Lorenz equations, and just getting back to the big picture again, we're trying to understand basically the experiment that I was describing, that hula hoop experiment. The idea is to build a test bed to play around with techniques for making predictions more accurate, because in the system that we're most concerned trying to predict the future state of right now, as a physical system, not relating to the humans, of course our behavior over the next 100 years will matter with respect to what the Earth does. But anyway, so making predictions of what the system are going to do are really hard because we can't tune any of the knobs and see what happens. You can't rerun experiments. You just have the computer to do experiments with. They're incredibly expensive because it takes like 2 weeks to run on a cluster that we have at UVM, a weather forecast. On the supercomputers that the Weather Service does it on, it takes more like 10, 20 minutes. But they're really expensive. So it'd be better to have, if you're going to try and figure out how to predict things more accurately, a model system or a toy climate system that you can do research with. So Lorenz's model from the 60s that you're looking at in your homework, that's the one that people always start with when they're trying to figure out, is this going to work? Am I going to be able to predict the future more accurately using this system? So let's see. So this is, right, we talked about the experiment and the observations. Cool. So just to give you a refresher, we have this hula hoop shaped tube. It's heat along the bottom half, cooled on the top. The fluid's frustrated in that state because warm stuff wants to rise, cold stuff wants to sink, and it can't go anywhere. That conducting state quickly becomes unstable as you dial up the heating in the bottom half or dial up the cooling in the bottom and the top half. So conduction gives way to convection, and this is one of those spiral sinks on either side of that Lorenz attractor picture. The three variables x, y, and z, remember, were x was the velocity on average in the loop, y was this temperature difference between A and B, and then the z variable was some deviation from the conducting temperature profile as you go from the bottom to the top. Cool. So this is so chaotic behavior is the attracting state for reasonably large values of this heating parameter. And we talked about a mechanism for creating that. And we have these fluid dynamic simulations of what's going on. So the fluid heats up in the bottom half, and there's some transient period where things are going to be kind of weird. It's rotating counterclockwise and then clockwise, and then settles in counterclockwise for a while. So one of the research questions that we try and answer is how predictable this behavior is. And so you see there's some regularity here. So there's an envelope of growing amplitude oscillations. And then once the amplitude gets big enough, the fluid will stop and turn and go back in the other direction. So one of the questions we asked was, what's that relationship like statistically? If we look at, weeks worth of behavior of this system, what is the relationship between, how long we call this a regime, how long it's going counterclockwise. What's the relationship between that length of time and maybe how big this deviation was just prior to the flow reversal? That's one of the types of questions that we ask. We also ask, how well does Lorenz's system, which again we're looking at the statistical averages of quantities that are varying dramatically as you look throughout this loop. So how well does a model like this do? This is the attractor you're playing around with your homework. How well does a model like that do at predicting something like, the bulk average velocity either in the computational fluid dynamics experiment or in the actual experimental data that we collect from the thing that's hanging on the wall that you saw the video of. Cool. So this idea of control theory, we get the pendulum standing on its head. This is a sketch for what it looks like in the atmosphere. We have some quantity that is changing over time that we'd like to, approximate the truth. We don't ever see it. We get observations of that quantity, maybe, from weather balloons or from satellites or, thermometers strapped to the bottom of planes. You get some collective observation, and then when we're going to then start a new forecast, we combine old forecasts with those observations to get our best guess for the current state. This is control theory right here. The Kalman filter does this sort of thing. It says, here are my observations of the truth. They're not right, but they're close. You know the statistics of the errors usually. There's an error covariance matrix associated with your observations. You know what the forecast did over some period of time, and so this is like a full 10 billion degrees of freedom forecast for the weather model, whereas this is only like 1 million observations or so. And then you combine those two. Maybe you have a whole host of these in ensemble. You find the best collection of forecasts that at particular places agree with your observations, and that gives you this sort of green star that's hard to see. That's the analysis. The analysis is your best guess of what the state is. And this is happening probably like 20 times a second for that pendulum that we just watched the video of. It's taking an observation of what the state of the thing is, and it's making a guess of what's going to happen next, and then it's adjusting the location or what the motor's going to do in order to keep close to, in that case, the thing, this red curve, what it's trying to do is keep it standing straight up. Cool, but the process is set up to try and synchronize the forecast with the observations. So here's an example experiment that so this is a UVM student who worked on this, Cameron Harris. He's a physics and math undergrad here. And what you're looking at is, there's a whole bunch of stuff here, but basically this is the computational fluid dynamics simulation flow rate, so that's like velocity, and then using those equations from Lorenz to try and predict what that CFD experiment is going to do. And what it's showing is that if you make observations a lot, so these observations are, so the background, these are forecasts and how every time you see a little triangle, an observation is being made, and the analysis is the adjusted version of the observations. The red curve, the truth, is sitting underneath here, and that's produced by one of these fancy CFD simulations, and the blue curve is forecast from this 3-variable Lorenz model like you're integrating on your homework. And it does really well. If you do these short forecasts with it, it does really well at predicting what's going to happen. And then if you relax the window, so it's looking for an observation every 2 minutes. It's just measuring this one thing, this one observation. And then if you make it longer, so it sort of breaks down, right? So the red curve is what actually happened in that CFD experiment, and the blue curves are all these forecasts. And sometimes, so here's an example where the forecast state says that the fluid's going to rotate clockwise, and what it actually did was rotate counterclockwise. And so there's a big failure, and the error gets really large there. And that's the sort of thing that would, in the case of the hurricane, you'll remember the cone of uncertainty, that's like the hurricane's wandered way outside the cone. And your ensemble of predictions, your probability of what's going to happen, it doesn't overlap. The truth doesn't fall within that. That's bad. But this is the idea. This is one of the mechanisms we try and use to build new ways to make predictions of these nonlinear systems. And here's one of these statistical results. So it's also from Cameron's paper that he worked on. So this is, for these time series, we're wondering, how long is a residency time? How long does the thing spend going one direction or the other? So I told you that happens aperiodically. Sometimes it's going clockwise. It might do that for a few minutes and then go counterclockwise for an hour. We tried to figure out what the statistical patterns were there. And this is a plot now of how large the previous oscillation amplitude was versus this axis here, versus how long the residency of the following regime was. And what you'll see is that, so these are things, this is an example where this whole collection here, where it only went in that direction one time. And then there's a step up here. And you see this has only gone in that direction twice. And this black cross corresponds to this piece of data. So there's like years worth of simulation in this picture. So this particular regime change from counterclockwise to clockwise is represented by one data point in here. So all of the regime changes are plotted in the picture. In this case, this is the oscillation amplitude. That's the x coordinate. So that's like right here. And then it did 2 trips around before the flow reversal. So that's why it's on the second step up. That was the residency time. This distance is the y coordinate. So doing that for all of these, every single time one of these flow reversals happens, we get this big picture. And so Lorenz's equations, if you did this, looking at Lorenz's equations, you would see this sort of steps, this set of steps. If you just ran that 3-variable ODE model for a while. This sort of stuff over here is not, the Lorenz model doesn't do this sort of thing. And so these are examples where the oscillation amplitude was really large and then it switched right away. And that doesn't happen. In Lorenz's equations, when you're winding away from one of these butterfly wings, if you go really far away and then switch, you kind of dive really in close to that unstable equilibrium on the other side, and it takes a long time to wind out. And then, if you're very far on that side, you'll dive in really close to the unstable equilibrium on the other side and wind out. And so that behavior doesn't happen for the fully resolved computational fluid dynamics version of this experiment, and it doesn't happen in the experiment itself either. And so that's a modeling error associated with trying to collapse all of this high-dimensional dynamical behavior down into these 3 variables. The colors of these dots are what happens when you put a little ball of initial conditions around that state in Lorenz's model and see how quickly the ball grows. So that's the Lyapunov exponent type experiment. So it's more and more unstable the further you go to the right, basically. So that's like, the further you go to the right, the more it gets close to this conducting state where it's very, very unstable at the origin, where there's a lot of energy going into the bottom half and a lot of energy going into the top half, and it's just kind of stuck there for a while. The longer it sits there like that before deciding which direction to go, the more energy it has stored up with which to do what it's going to do. And so that's why you get this gradient from, the most predictable over here on the left to the least predictable over here on the right. Any questions about this picture? Okay. One of the other cool things that this Kalman filter can do is, you'll remember one of the things we talked about was state reconstruction, where you can observe one of a particular set of variables and then reconstruct the others by plotting time-delayed versions of it. So the Kalman filter actually can observe just one, let's say the velocity variable x from this CFD experiment, and infer what the y and z variables are from this matrix algebra that sits inside of the Kalman filter. So here's an example where the conducting state is down near the origin, it's down near here, and the Lorenz model wants to leave there very quickly, which is why these things are all very red. But the Kalman filter knows it's getting observations of just one of these 3 variables, and it knows that even though that state is very unstable, the CFD simulation is doing that. It's sitting close to that very unstable equilibrium at the origin, and it's able to infer what the other states would be. So the Lorenz model wouldn't do this, but the Kalman filter knows about the structure of the behavior near there, and has the thing sit there for a while, even though the Lorenz model doesn't want it to. Cool. So I showed you a couple simulations of this. Right. But getting back to the point, the idea is we're trying to make a test bed for these predictions, so you can develop new techniques for making the forecast more accurate. That's the idea. So I'm going to show you a few other experiments that we've done related to the shadowing concept from homework 10. You worked in that problem, in that homework set about trying to figure out, we have these computer simulations and we iterate maps and we get a picture, but we're talking about chaotic systems. So when the computer makes an approximation of the state and then you iterate the differential equation in this case, or the map, the trajectory that you're on isn't the one that you started on, and that happens every single step. And what are the consequences of that? So it turned out, at the end of that homework, it turned out it was okay, like the picture was okay. There was a criteria, though. The criteria was that the number of positive and negative Lyapunov exponents and their orientations relative to each other was constant. And we didn't talk about that much in the homework, but that was a requirement, if you'll recall, because you have this stretching going on all the time, and even though, you have some positive Lyapunov exponent and there's a chaotic, the orbit could be chaotic, you could always start closer to the one that you started, the initial condition that was the V0 or whatever at the very beginning. You could always start really close to that if you wanted to stay close for a while. That doesn't actually work for a lot of the systems that matter. So I'm going to tell you a little bit about why that breaks down. I've said all along that, it's this concept of stretching and folding is important. The stretching is the one direction, folding is the other. Negative Lyapunov exponent. So I want you to imagine now in this, a lot of that discussion was about these maps. And now we're talking about differential equations. So we have these continuous curves in time. So this might be something like, the temperature or the pressure outside. The blue curve is the truth that we don't ever actually see. We just get observations of it, and then we make forecasts. That's what these red curves are. Cool. So you see here, so the blue curve, the thing we don't see, we'd like to be able to be near it in this state space. So imagine we have, let's say, like temperature and pressure here. And so the system's evolving, and I'd like to be able to make a forecast that stays nearby. And I get observations of this truth, so maybe I start near them. And we know what happens when I take a little ball around the state space and I map it forward, right? We get this sort of, the nonlinear thing is some wiggly shape that's, it's more wiggly the longer out you go in time, and it's approximated by an ellipse whose volume I can compute using statistics on the Jacobian of the map or the model from back here. And you're going to do this on your homework for the Lorenz equations. So this axis, this ellipse right here has in it some forecasts that are still good. These ones down here are not good anymore. Why are the forecasts down here not good? Like the red, if I want to know what the blue dot is going to do, that's the state whose future I'd like to predict. Why is this a bad forecast down here? Yeah, if like a reasonable forecast is something near the blue dot, then I want to stay up here. And this has some forecasts that have stayed close. So these are the reasonable estimates that have survived. I have small uncertainty and large uncertainty, so that's like one positive and one negative of these exponents, these Lyapunov exponents. So I have some good predictions, and that's good. And if I were trying to shadow the dynamical system, I would want to keep having those. So even if the axes turn a little bit, I continue to see shrinking in one direction and stretching in the other, I still have some forecasts that are good. And this will work forever, provided I always have that one axis shrinking and one axis stretching. That's what this whole shadowing concept is about. And that's why you can trust the orbits that you've seen on the computer for most of the things we've done. So if I did, if I looked at I did Gram-Schmidt orthogonalization on that ellipse, the z's, remember turning into the y's, I would see that these were the axes that were expanding and contracting. But if I then went and, this is hyperbolic. I got my taffy in here again. This is good. It's going to go? Nice. Not go. Come on. Nice. Okay. So remember, the idea of the taffy is, as long as I have stretching happening in one direction, folding happening in the other, then if I really want to know what happens to one little speck of that food coloring dye that I dropped in, I can always wind the tape back and find something really close to it And even though there's stretching going on, I can stay close to it forever as long as I go back and get close wherever I begin. It's going to stretch a lot, but so these systems are called hyperbolic, ones where the Lyapunov exponents don't change in dimension. How many are positive, how many are negative. It is the case that sometimes these dynamical systems that you'll wander into some region of the state space where it's like somebody grabs the taffy and starts pulling it into a sheet instead of it having this one direction that's positive and one negative. And so when that happens, we end up with, so we have two, in this case, we have two unstable dimensions, two positive Lyapunov exponents, so things are stretching. And then, like this distance right here, which, so if I think about this, previously this distance was contracting, and so my forecasts and my truth, they're still kind of constrained with respect to each other. The shrinking is happening in this direction. But if this then starts to expand, if I then took this axis and just start pulling it apart, then I'm going to end up with all of these forecasts that were good here. If this direction starts stretching, this distance between my best forecast and the truth, that's going to grow. And so I end up with an ellipse over here of forecasts that used to be good that aren't good anymore because of this new direction of stretching. Okay, so shadowing has failed. I don't have any forecasts over here that are within my uncertainty ball of the truth. And this is that hurricane problem. That's where, that I end up with a hurricane doing something that's outside of my cone of uncertainty. So, so this is a thing that happens in these dynamical systems, and that we've proposed a solution to. So Jim York, who's the author of this book, and I worked on this when I was in grad school. We worked on a solution to this problem that we called, instead of shadowing, we called it stalking. And the concept is we take this ellipse. Imagine it's got one direction shrinking, one's expanding, and we artificially inject some extra uncertainty in the directions that are shrinking. So we talked about this SVD, and you get these axes of the ellipse, and some of them have shrunk. We're saying, puff those up a little bit every time, maybe like every 10 time steps of your integration, or every time you iterate the map, so to speak. Small amount, like 1%, 2%, 5% of that width. And the idea here is that, well, for one, if this direction continues to shrink, we're injecting uncertainty into something, and it gets taken away right away, basically. It's like I'm adding humidity to the desert. It just gets absorbed. It's strongly contracting, and so that additional uncertainty effectively disappears quickly if it's not, if nothing happens. However, if we end up in the situation like this where, I'm right here and my ellipse is too thin, it doesn't have the truth in it, and then this direction starts to stretch away, if in this case, if we've made this inflation and I have the truth inside my ellipse, and then this direction starts stretching, then I'm going to have some forecasts that stay close. So that's the idea. It doesn't harm the forecast much because it's like I'm making this hurricane cone bigger. Of course, it would be more likely to have the hurricane go in it, but that's getting damped away every time by the fact that this direction is shrinking, unless it starts to stretch, in which case it helps. So here's the cartoon version of what would happen in these two situations. So here in the top, we'd see we're injecting a little bit of uncertainty into that smaller direction of the ellipse, and it contains the truth, and then we get this huge probability distribution. Everything's a lot less likely, but the truth is one of our estimates. And so we get a forecast, which is the pink stuff here, that stays close for longer. And so it's stalked the truth instead of shadowing the truth. That's the idea. Yeah? This one here? Yeah, so I'm imagining I turned on this stalking procedure like in between here and here. Yeah. And remember, you don't know what this is. You don't know ever where the blue dot is. You just know what the pink dots are, and then you're doing linear algebra on the pink. And then when it's over, you can look and see, oh, it worked. Or it didn't work. Okay. So, yeah, SVD. This is basically what we do is we take these SVD modes that we talked about. This is the singular value. The second one that's we've noticed is smaller than it used to be, and we add a little bit to it. That's the idea. I'm going to show you some results for this experiment. So one of the other toy models that we use is similar to this. It's also actually, Lorenz is also the person who proposed this model too. It's like you're sort of looking down on the North Pole, and this is a latitude band. Let's say it's mid-latitudes. Like here, we're just south of the 45th latitude here in Vermont. So we have this latitude band, and then you're looking at different locations, longitudes around it. Okay, so that's these x's. So imagine I had 8 locations on a particular latitude band that I wanted to model. And then each of them has their own little local, small-scale, high-frequency behavior that's represented by these y's. And that's stuff that doesn't get resolved in the equations for the x's. And this is, so this is a toy model. Kerry Emanuel is a hurricane modeler at MIT. This is a toy model for the atmosphere that they proposed that basically has the advection equation for motion and some forcing, is energy being put in, and then this coupling term over here. Similar thing for the y variables, the high-frequency behavior, and it couples back into the x. And then one interesting thing about this is it's you can choose the dimension that you want. So I could say I want 100 of these x's, and each of them is going to have 7 y's. Or I could say I want 8 x's, and each of them is going to have 4 y's. And so it's a system that you can dial the amount of nonlinearity you want in it. You can, and the forcing is the parameter that you get interesting bifurcations with. Yeah, Renee. Awesome. Yeah, good question. So you could actually have z's, let's say, coupled to the y's, and people do that sort of thing where they have a hierarchy of behaviors in an attempt to separate timescales usually. So if you know that there's some feedback on a slow timescale, you model that with one set of equations, and then the high frequency behavior and if there's a natural separation, then that usually makes sense to do that sort of thing. Yeah. The way we use this is basically we imagine these x's as the thing that we can measure. And then the y's is, so we'll create a true state of an atmosphere by integrating this for a long time. So let's say we get, time series of 8 x's and time series of these 32 y's for a long time, like several years, and then call that the truth. And then we go back and try and model the x's without the y's. So remove this term, and you just have the x's, and then you say, how well can I forecast the true system, which has all this stuff going on in it, with just the observed behavior of the x's? How well can I model it? And in practice, that's a bit like the situation we're in, right? We can't model every little bit of the atmosphere, but we can aggregate it into larger scale behavior, and that's typically what's done. So I think I have some animations of what this looks like. So here's an animation where, again, you're looking down on the north, sort of on the North Pole, and then what's being plotted here, these blue dots, each of them is, I guess there are 35 x variables in this particular animation. And so there's 35 of these x's. Each of them has 10 y's. The y's are the green behavior. This animation was made by Morgan Frank, who was a math and CS major here and did a master's degree. He's now at the Media Lab at MIT, working on a PhD. So each of these, you can see there's sort of waves moving from, the waves moving clockwise around here. I guess, let's watch one more time. And then the y's you can't really see because their amplitude's a lot smaller. So the amplitudes of the y's are smaller, but they feed back. Stuff going on in the y, you'll see them wiggle a lot when the x's are large. So when you see one of the x variables get big, you'll see the y variables get big as well. So there's feedback in both directions. And the value of that the x value is just mapped so that its minimum is at the center of the picture. It's a way to visualize 40 or 35 dimensional data. Anyway, so what we'll do is we'll take simulations of this model and then try and make predictions of what it's going to do. And it has, like you might imagine, nonlinear system. It has parameter values that produce very stable behavior. So there are modes of this with particular combinations of how many dimensions of x and y there are, where all of the energy gets sort of aggregated and synchronized, and you get these nice patterns. And so this is stable behavior that any initial condition would result in. But then you also get the nonlinear version down there on the right. So So there's modes of this model that produce very stable and repetitive behavior, and then very nonlinear, aperiodic, chaotic dynamics down here on the right. This is sort of the stuff we usually want to predict. So we want to predict what the blue dots are going to do and ignore the green, even though the blue depends on the green. So I said that this idea of inflation of the ellipse is how we combat that change in the number of negative or positive Lyapunov exponents. So this is what an outcome of that procedure looks like for this model. So the black curve is what the truth did, and then these gray curves are all forecasts of that truth. They don't know about the black curve. The gray curves don't. All the gray curves know about is the equations of the x. The black curve knows about the x and the y. This is work done by Ross Lieblappen, who was a master's student here also a few years ago. And so here's what it looks like. You have this set of forecasts. The hurricane is outside the cone right here. The truth, which we don't observe, it's not close to the forecasts. And then at this spot in time, what happens is we pause, we take the ellipse that it's now in 40 dimensions, if there are 40 ensemble members, right? We take that ellipse and we're going to inflate directions of it that have been shrinking. It's like saying the model is becoming really certain, it's probably wrong, spread it out a little bit. And that happens right here. And what happens then is that little inflation, again, which knows, these gray curves know nothing about the black curve. The observations, there's no data assimilation here like there was 20 minutes ago where we're observing the truth and adjusting. That's not happening here. It's a free running forecast. Spread it out, and then it happens a second time. And you see here now that the difference between our ensemble members collectively, the truth looks like the median ensemble member all of a sudden, just after two of these little inflation techniques. So this is the idea behind trying to deal with this shadowing failure when the unstable dimension changes in these dynamical systems. So it works more often than it doesn't work. More stuff above 0 than below. And yeah, questions about that? Any questions? We're trying to figure out how to make forecasts more accurate. The forecasts are probabilistic in nature, a discrete estimate of some probability distribution because we have computers we have to run these things on, and we can only do a few perturbations of our best guess of the atmosphere. Easier to develop this stuff on lower dimensional models. I've shown you a few examples. This Lorenz model you're working with on your homework is one of them. It's pretty cool. Yeah? Yes. 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 It's a hedge. So what Sven's saying is, there's modeling error. You know that chaotic systems spread apart from each other, and so we need a host of forecasts, not just one. And the way that dynamical systems work is the folding aspect is going to bring our forecasts together in directions that are effectively the forecasts are becoming more certain about. But if the true system is not actually shrinking Lyapunov exponent negative in that direction, we're going to have a disaster. Our forecast is going to be really bad. And that happens a lot. And so the idea of the stalking is you hedge against that happening by injecting uncertainty every so often, which has the effect then of if that direction continues shrinking, it doesn't really have much effect at all because that uncertainty you're injecting just gets damped away. But if it does happen to stretch away, then you have a forecast that remains closed for longer. Yeah. Good question. So how do you decide how much to puff out that ensemble or ellipse? We did experiments just to try and see, all right, is it 0.1% of that singular value, or is it 1%, or is it 10%? If you did it 100%, that would be like saying, all right, everything is possible, which isn't helpful. And also there are some technicalities, as you might imagine. These ellipses aren't exactly what the nonlinear behavior is going to look like too. So basically we found that let's see. We found that more inflation will make the forecasts, more likely to at least one ensemble member be accurate for longer, but it also makes the rest of the forecast worse, right? Because you're also sending states to the other side of the ellipse that aren't close to the truth. You're saying that you're giving those equal weight also. And so really what it's designed to do is keep at least one forecast close. It's good at that, but it's also going to dilute every other probably, likelihood as well. So it's absolutely a parameter that you would have to tune for a particular system. Yeah. Other questions? Yeah.
But so if you don't know really what's happening with the true state,
Yeah.
predict it, how do you know which would be the good point to be looking at?
Good. Yes. So the question is, if you don't ever see the truth before you make the forecast, how do you know which forecast is going to end up being the one closer? And the answer is you don't. But the idea is we're trying to build that cone of uncertainty, and you want the truth to be in the cone. And effectively what we're saying is, you're taking that cone and in the state space of the model, artificially making it a little bigger in directions in which the models are more certain. Because most of the time that'll be fine, and it'll just those dimensions will get damped away. But occasionally it could matter, and we'll end up with the cone containing what ends up happening, which ultimately is, like you'd want that to happen. Yeah. Other questions? Okay. So I have a couple things I wanted to write down about this this Lorenz attractor again. So we have so you'll recall we have this, these three variables, x, y, and z, that produce this really cool behavior. You're going to make some pictures in your homework. And one of the cool things that Lorenz did, and you're going to do this as well, is try and relate the behavior here to the tent map. So what he did was, you'll remember the z variable here is that it's the deviation from, vertically from a conducting temperature profile. And the z variable, as a function of time, if I plotted it for this system, would look, so this is 0 down here. It would look something like this. So it's going to have some inherent frequency with which it's oscillating. But for a chaotic trajectory of this set of equations, you won't see, repetition here in the heights. So what Lorenz did, and this is really a remarkable idea, is he said, all right, here's what we're going to do. We're going to look at successive maxima of this time series. A bit like taking some sort of stroboscopic view of a continuous dynamical system, because we have tools in discrete dynamical systems that we like to use. And so here's if that's the first one, that's the second one, that's the third, that's the fourth. So these are successive maxima of this z variable. So call that z1, z2, z3, and they have times associated with them, and they're not exactly some delta t away from each other, but they're close. Okay, and then what he did was he said, let's map z at some time I or iterate I against where it goes. And this is a way to condense all of this information, this high dimensional behavior down into a single map. So let's look, z1 and z2. So z1 looks smaller than z2. So that means I'm going to put this first one, this first x is going to go there. That's this corresponding to this pair of points. And then z2 is much smaller, is much bigger than z3. So 2, 3, that's like over here. And then Z3 is much smaller than Z4. So that's like over here. And he just filled in all these dots for different trajectories of this Z. And this is the picture he got. And I'm going to show you what it looks like, and you're making this on your homework. Each plotted dot on the tent-like map is a pair of maximum Z coordinates of loops of the trajectory, one following the other. So, this could have looked like some crazy scatter plot that you'd want to, find the correlation of, and it would be a small number. It'd be some sort of crazy dust of nonsense. But it falls on a very low-dimensional curve. I mean, it looks like the tent map. How many fixed points does this thing have? Imagine this were a map. How many fixed points does it appear to have? 1. Does it look stable? No, it looks unstable. So there's some Z value here, which is a situation where these two heights are the same as each other. Okay? So that would be a period 1 orbit of this. If the fluid was doing the same thing over and over again, it would rotate once and then rotate. Which is a state that we can observe. In this case, it's not stable. So if we started near there, we would wind away if we were drawing a cobweb plot, right? No other fixed points on here, which means, do you think there'll be period 2 orbits, maybe, or period 3 orbits? Does the tent map have those things? The tent map does have those things. They're all unstable. And so does this system. There are unstable equilibrium of higher periods and a whole bifurcation diagram to create, which you'll do on your homework too. Yeah, super cool. So there's structure. There is structure hiding in here. You see this time series, you think, oh well, it looks like there's nothing predictable what the next maxima is going to look like with respect to the previous. But they occupy a very small collection of points in this state space here. Cool. So then what Lorenz did is he said, okay, I'm just going to take this this behavior, the long-term behavior of a particular orbit, which this picture traces out just fine, and I'm going to plot it as a function of this parameter r. So r is how much energy is being put in. And you'll remember when r is small, conduction is the stable state. It just sits there. And then convection becomes stable in either direction, and then that becomes unstable, and it rotates aperiodically like this. And so this is the picture that you'll also make of the what the bifurcation diagram looks like. And there's stuff to the left. So left of 25, this thing looks like, so Z is 0 for a while, and then at 1, it leaves 0 and comes up like this, and then there's going to be some stuff happening around 13, I think, and then it turns into what you see here. And this is the Z variable. So which one is this? So this is for some value of R, probably it's around 28. So that's like here. You see this collection of dust here. That's what the Y coordinate, all those Z's trace out. If we collapse that tent map looking thing down onto one axis, it would be this dust right here. Periodic windows for large R, a period collapsing back down to 4, 2, 1. What's going on out here? That's when there's so much energy being put into the bottom half, so much energy being taken out of the top half, that the thing becomes stable again, and so it rotates convection in either direction, stable. When there's 2, that's up here. When there's 2, that means it's, sort of spinning around once and then slowing down and then spinning around once again and slowing down. And it's doing that periodically. So there's an oscillation that's stable. This is incredible. Pick a parameter value for this R. You trace this out, and you're going to be working on this in MATLAB for your homework. At least you know what you're shooting for. That's good. Questions about this?
What does the middle periodic window correspond to?
Yeah, what's going on in here? So this is, if we think about, remember with the tent map, if we plotted, or the logistic maps bifurcation diagram is similar. You end up with these windows inside that result from, higher iterates of T or G having new behavior that wasn't there before. So you have a state, you can have a bifurcation where, let's say it's G8, comes up and touches and is briefly tangent to y equals x, pushes through it, and you end up with sinks that you weren't there before that attract things nearby. And as you're dialing the parameter, if some higher iterate of the function pushes through y equals x, you get a bifurcation that results, a saddle node bifurcation, that can produce, for a while, sinks. And then the slope, as you dial it, the slope will go up from that sink, will go above 1 in magnitude, and you get period doubling again. And so that can happen in either direction here, depending on the parameter, right? That happened in the logistic map, only going in this other direction, but yeah.
I'm trying to see if I can follow any sort of curve to scatter points.
Yes.
It looks like it goes up and then tries to completely scatter.
This one up here.
Yeah. And then it comes back down.
Down here, yeah.
Yeah, this seems to actually connect it.
Yes. Yes. Cool, huh? I have no idea why it does that. Yeah, so that you'll recall that in the logistic map bifurcation diagram, there are all these interesting curves kind of sitting in the noise. There's order in there. And they were a result of the state spending more time in some parts of 0 to 1 than in other parts. For example, if you land really close to a source that's weak, you can spend a lot of time winding away from that source. And as the parameter changes, it probably doesn't change too quickly, that strength of that source. And so that would be one mechanism to produce, a distinct ridge in these bifurcation diagrams that is itself moving as you dial the parameter. Some source that's really weak in repelling points, slopes like 1.0001 or something, that things stay close to for a while, but they don't stay there forever. Right. So then this z value, there's some maximum at which the chaotic state will produce, there's some peak height that this won't go above based on the energy you're giving it. And that's growing with R. You can see that, right? As this thing's going up as you move and make R bigger. So there's more energy going in. This z value can get bigger and bigger. But then you're noticing that it comes back down here. Yeah. So there's some, I don't know why that's happening. There's something going on there. I'm sure there's a good reason, and we could sort it out if we really wanted to. Yeah.
So there's something very different going on in those windows there than there were when we were talking about windows in the other bifurcations diagrams.
Do you mean because they're backwards? Or because you see something qualitatively different, or?
Well, weren't you saying the bifurcation diagrams we were looking at before, that it was that the computer was just slipping onto an orbit?
Right. So, no, we were talking about the period 3 window and how period 3 implies chaos. And that there are chaotic orbits there. They're inaccessible for the computer. Yep. So that's true, but there also are attracting behaviors that measure, some volume of the state space worth of conditions. So yeah, if there's a period 3 orbit, there's chaos, but it might be a measure 0 set of points that do that, but they're chaotic anyway. Yeah, the particulars of these bifurcation diagrams, there are people who try and figure out, well, what's going on with this thing right here? You could spend some time trying to figure that out. And in this case, there's no function. There's just the solution to a differential equation. So it would be harder to interpret. But you could approximate, and people do this sort of thing, you approximate this with a functional form and then take higher iterates of that function and see what happens to it. Other questions? Okay. All right, I think that's going to be good for now, and I'm going to give you a couple minutes to fill out your question. Yes, I will give you homework 11 on Thursday and solutions. Yes. So you got 5 minutes or so left. I am going to, so I tweeted the link to the course evaluation page, and we have been instructed, faculty at UVM, to give you a few minutes in class to respond on your mobile device, if you have one. So you should do that. And I'm supposed to step out of the room while you do it. So